Okay, thank you very much. Um, so it's a pleasure to talk about EPOS4 here, and I will not so much talk about results, but more about the new concepts, because EPOS4 is quite new and kind of the concepts are quite different compared to other models. So I think this should be known. Let me start with a spacetime picture. And it's actually a spacetime picture for proton nucleus or nucleus at very high energies. So we start here at early times with a projectile and the nucleus and the target, and they approach each other. And then we have what we call primary interactions. And this is corresponds to a point-like overlap. And this point-like, that's really important. And this is true not only in PP scattering, but also in proton-nucleus and nucleus-nucleus scattering, because we have very large gamma factors. Therefore, the nuclei are very small and the overlap zone, so when the two nuclei pass through each other, is essentially zero. And this is later followed by, at least in our picture, by a quark-gluon plasma phase, later hadronic phase, and so on, what we call then secondary interactions. I will more focus on the primary interactions. I mean, it's only point-like and happens instantaneously, but it's quite complex, and this I want to discuss here. Now, the picture is actually not really correct. Actually, one has to start much earlier. So more realistic space-time pictures like this. So we have a splitting into multiple partons, so-called parton evolution, which starts already very early, long in advance, long before the red point. And this is again true because we have large gamma factors. Actually, these large gamma factors are very important for high energy collisions. And the interaction region is still just a point, but kind of the preparation of the whole collision with parton evolution, that takes a long time, and that starts much earlier. So if we have multiple scatterings, all this long evolution has to be taken into account. So the only way it can happen, they must happen in parallel. If we have proton nucleus or nucleus nucleus and the interaction zone is a point, that also means that all the interaction have to be instantaneously, so in parallel. So that's very important, and that's kind of the crucial thing in the EPOS. So the EPOS4 philosophy concerning the primary interactions avoid sequential scatterings, and this concerns both parton-parton scattering in PP, and this we know that it's important at very high energies. There are multiple scatterings, and also that concerns nucleon-nucleon interactions in PA or in nucleus-nucleus scattering. So do multiple scattering rigorously in parallel, and that's not so easy. And this I will discuss about. And this sounds really trivial, but it's really important to respect the rule. The Monte Carlo should really correspond to the underlying theory, which is very often really not the case. And I will come to this back later several times. So I do not want to make a technical talk here, and so I have more qualitative arguments, many pictures, but nevertheless, I mean, there are some formulas behind, and I still need to explain some symbols. We talk about scattering, so we have, first of all, the elastic scattering T matrix, which is at very high energies. That's relativistic. So the kind of natural variables are the S and T. So the usual Mandelstam variables for the energy squared and the transverse momentum squared. Now, much more useful and for our purposes is so-called impact parameter representation, where one considers a Fourier transform of this T with respect to the momentum transfer divided by 2S. And I call this T italic. And the arguments are still S and now B, the impact parameter. Now, and we are more interested in inelastic scatterings, and there one uses 2 times imaginary part of T, which represents now an inelastic scattering. The T is an elastic scattering, the G, the 2 times imaginary T, that represents an inelastic scattering. And the last quantity are the sigma tildes. Now, for all in this impact parameter representation, for all proton-proton cross-sections, one can write them as an integral over impact parameter times something what I call sigma tilde. So the sigma tilde you will see in the future, these are all objects which need to be integrated over to get the cross-section. So they are dimensionless, and there's something like the probability of an interaction at a given impact parameter. This is also true for nucleus-nucleus scattering here on the bottom. And there you simply need to integrate not only over the impact parameter, but also over the positions of the nucleons of the two nuclei. Now, the formulas are very simple in terms of the sigma tildes, which you see right away. So let's, as a warm-up, look at the Gribov-Regge approach. And I think everybody interested in high-energy interactions should know about that. And here are the names behind: Abramovsky, Gribov, Cancelli, Lipatov, done in 50 years ago. But nevertheless, it's still up to date in the sense that here they already understood the importance of scattering in parallel. So in PP scattering, it was found necessary to consider multiple scattering already at that time, and this strictly done in parallel. Now the picture is shown here, and here the boxes represent, each box represents an inelastic subscattering. So here we have two subscatterings, and they producing each one a chain of particles. At the time unknown how precisely, I mean the structure was unknown, it was before QCD. But even nowadays, this picture, there is no contradiction, even if there's a long preparation of the collision. So the collision can take 100 Fermi of preparation. If they are completely in parallel, there's no contradiction. Now, in this picture, the cross-section are expressed in terms of weights P, depending on this G. So the G is the elementary inelastic process. So this sigma tilde for PP, for the inelastic scattering, is then given in terms of a G to the power M, and this represents M-fold parallel scattering. And these PMs, they can be interpreted as probabilities. And a similar formula is true for nucleus-nucleus scattering, which includes proton nucleus, by the way. So we have a similar formula, so just a product over many pairs of possible nuclear-nucleon interactions. And we still get these expressions which can be interpreted as probabilities, which is very useful because this is kind of then the basis of the Monte Carlo. Now, the EPOS4 improvement step number 1. This is the implementation of energy momentum conservation, referred to as, here in my talk, as Gribov-Regge plus. So the plus stands for plus energy momentum conservation. For certain observables, this is not so important. For example, for total cross-section, essentially it's important to make a projection on top of each other. For other observables, it's crucial, like for particle production. And this is what we are interested in. So I think for us, it's really crucial to consider this energy sharing. Now, it is necessary as a solid basis for Monte Carlo, because in the non-Monte Carlo, we have to do energy momentum conservation. Nobody will use a code which doesn't do that. But the other underlying theory should do the same to be compatible. Now, how is it done in EPOS4, or in EPOS actually already? Now in proton-proton or in nucleon-nucleon, for each nucleon-nucleon scattering in nucleus-nucleus, we have new variables, and these are the light cone momentum fractions x plus and x minus for each sub-scattering. So each sub-scattering is characterized by an x plus and an x minus, so which gives the energy of the sub-process. And we have total energy momentum conservation because we have to consider now also the remnants, which is the red line here, with a momentum fraction x plus here and x minus on the other side. And the x remnant, they take just 1 minus the sum of all the x's which is going into the scattering. So we have complete energy momentum conservation. Now, in this picture, the cross-section are still expressed in terms of weights P of configurations K, which are now a little bit more complex. So we have not only the MKs from the Gribov-Regge picture, which are the MK subscatterings per pair K, but in addition we have this light cone momentum fractions for each of this particular subscatterings. So it's quite complex, but the point is a very solid basis of the Monte Carlo now. So one determines the K, so this complete multiple scattering configuration according to the PK instantaneously. That's very important. Instantaneously, there are no sequences. There's nothing like a first and a second interactions. Everything is completely in parallel. So that was our aim. And in this way, we can realize it. It's a bit complicated to do it technically, but it's doable. And so here we have really 100% underlying theory is really what we do then in the Monte Carlo. There are no additional if statements to conserve whatsoever in the Monte Carlo. Now the EPOS4 improvement step number 2. So far, it's a general framework based on some G, which is a box, but the G represents a subscattering. And now we make the links with QCD, and we say the G should be GQCD. So at the beginning, we thought, what else could it be? So the GQCD represents parton-parton scattering based on perturbable QCD, including the Diglab evolution. And so all this is calculable. And we have a long evolution there. Actually, the first paper, there were also Sergey and Tanguy, who are in the audience here, involved in 2001. And kind of the more recent work where we spent more attention on heavy flavor parts, and this has been published last year. And so, okay, so this represents now the link to QCD, because we know this nowadays in comparison to what people knew 50 years ago. So what we do, essentially, we replace the boxes, which are just black boxes, by something concrete, which is expressed in terms of quarks and gluons, kind of compatible with QCD. Now we compute and tabulate modules like the QCD evolution, the Born cross-sections, the vertices, which then allow to evaluate these diagrams as just convolutions. So all this is, again, complicated, but it's doable. Now, there are different ways to rearrange the modules, and one possibility is to define and tabulate parton distribution functions from these different elements, and this then allows to compute the jet cross-section versus PT in the usual way, the usual formula which everybody uses. Just here we take our own PDFs, which are based on elements from the EPOS formalism. And if we do that, and then we plot here, as shown, as a function of the transverse momentum, we plot the inclusive cross-section. The red line is what we get from our EPOS calculation. It's not a Monte Carlo, it's just a calculation, just an integral. The dots here are coming from Atlas, from a 2018 publication. And the green line, I hope you can see it. This is kind of another PQCD calculation based on the CTEC parton distribution function, and everything is very close to each other. So this looks promising for the moment. Of course, we have parameters. I mean, in our kind of modules, these vertices, this is more or less the same thing as the initial condition for the parton distribution function, but we cannot use directly parton distribution functions. These are kind of elements of our approach. But we can fit or fix all our parameters such that at the end it's the same as people get using this usual parton distribution functions. Now it looks very good, but so far we consider just one single subscattering, and this works already. Now in the Gribov-Reddy approach, and that is maybe not so well known, but very important, the full multiple scattering scenario is equal to a single one for inclusive cross-section. This is related to this famous AGK cancellations. So the AB, the nucleus cross-section, is 8 times B times the single parton scattering. Translated for PP means the PP cross-section is equal to the single scattering cross-section. That's a very strong statement. And the question is, and since the single scattering works already, so we need this in order to have something which works also for multiple scattering. So does this AGK hold in our case? And we can easily check that. We simply make a simulation and we do the full multiple scattering, and then we compute the AB cross-section, inclusive cross-section, d sigma over dpt divided by A times B times the single scattering. And if AGK holds, this should be 1. And now you look at the plot, what we get, it's far from 1. So only for PP, we have a problem. It's really far, it drops a lot. And for lead it's even worse. It goes down to 0.2 instead of 1. So it's really completely wrong. So AGK is badly violated. So we have kind of the strange situation. So we add something which we think really need to be added, but kind of things do not really look good. Now, inclusive particle spectra like PT, they are determined by the distribution of the light cone momenta x plus and x minus of the subscatterings. as indicated here on the plot. So the X plus, X minus, this is the S, the energy squared of the scattering divided by the total S. So it's the relative energy squared. And it's clear that in order to produce a high PT parton here from the hard process, you need a high energy. And if the energy is suppressed, then this will suppress also the PT, high PT production. And now you see how the energy sharing works. So let's consider here in the picture, given subscattering, which kind of makes a scattering between the projectile nuclei I and the target nucleon J. And now there may be different scatterings which are connected to the same nucleons. And I indicate this here by the red dots and by the blue dots. And then I define something which I call the connection number N-con, which is the sum of the red and the blue points divided by 2. Now, the importance of this number is if it's 1, then we have an isolated pomeron, a single scattering. If it's bigger than 1, then we have several scatterings which compete concerning the total energy. They have to share the energy. And this can be easily seen if I look at the distribution of this variable XPE, which is the energy squared of the single scattering. Now, the reference curve is the red curve here as a function of XPE. But now if you consider a distribution of this XPE for an N-con bigger than 1, which means now we have the situation like in the picture here, we have many other scatterings which compete with concerning energy conservation, then a single scattering cannot kind of have all the energy which we may have if there was only a single one. So we get naturally a suppression at large X, and there's nothing one can do about it. So it must be like that always. So what is the consequences for the PT distribution? So if we have a large connection number, that means the large XPEs are suppressed, and that means the large PTs are suppressed. And so we have this situation here for the distribution as a function of PT. So for N-con, the reference curve is in red. And now for the N-con bigger than 1, if we have additional scatterings in parallel, this will lower the curve. And since the minimum bias is in a superposition of several of these, they can never be equal to the N-con equal 1 case. They are always below, and this must be like that. So from energy conservation, you cannot avoid something like that. So we get, in this way, we get the violation of AGK. So now we understand why. So and now we understand it's not a question of a wrong choice of parameters, what we thought for a long time. It's really a fundamental problem. Now, to make further progress, we define a deformation, which is just the ratio of these two functions for the N-con and for the N-con equal 1, which we call our deformation, our deformation function. And the fact that this is different from 1 creates the problem. If it would be 1, then everything would be fine. If it's different from 1, then we violate this AGK. Now, at least we are able actually to parameterize this. So we have a problem, but we can, to some extent, parameterize the problem. So on the right-hand side, you see this kind of deformation function in red, the simulation. The black points are the parameterization, and it's very good. And you see that all them for different systems, different energies, they look like that. So always for large X, we get here a reduction of suppression, finally, of high large X values. Now this, after this, the R deform as a function of this connection numbers and as a function of X, this can be considered to be known, at least. Now there are, fortunately, actually, 2 problems. Concerning this single scattering expression G, our elementary building block of the multiple scattering, this is, here we have the assumption G equal GQCD, which seems to be wrong. So we always thought it must be like that. It's kind of natural, but it seems not. So it seems to be wrong. And we have this AGK problem, and we cannot avoid it. So it's not a question of parameter choices. On the other hand, we also don't have nonlinear effects so far. And now we have to solve these 2 problems in parallel, actually. Now, the EPOS4 improvement step 3. Now we add saturation. So actually there are saturation phenomena. So here on the projectile and on the target side, there are at very high energies additional processes, like we may have 2 gluons and they fuse before then the lateral develops. And Now, they may be summarized, this we learned in the last 20 years, by so-called saturation scales, which kind of suppress particle production below these scales. This suggests that we treat these nonlinear effects by introducing saturation scales Q sat as the lower limit Q0 of the virtualities in the Deglab evolutions. So, and in order to prepare that, we compute and tabulate the GQCD. Now, not only as a function of the usual variables, but we add a new variable, which is the cutoff. So the cutoff now is a variable. It's not just a constant, but it's really a variable, and different values are possible. And then here comes the most important formula then. So we do not have simply G equal GQCD, but the connection between the G from the multiple scattering approach and the GQCD, which is computable based on coarse inclusions and PQCD. This is now the following. The GQCD is up to normalization constant equal to the GQCD divided by this deformation function. This is why we needed to parameterize it. But the important point is now in the GQCD, the cutoff is now replaced by the saturation scale. And now comes the most important thing. So this has to be such that the G on the left-hand side does not depend on the N-con, whereas the R deform, as I showed you, depends strongly on this N-connect. And this has to be completely absorbed by the saturation scale. And this is really what finally makes the job. And there were also we struggled for many, many years, and there were several publications already in this direction, but it took us a long time to really understand this fully. And I think now we are there. And now based on that, and I think really it's difficult to imagine something different if you really understand how the problems arrived, then you can show rigorously that the inclusive cross-section for the dx plus dx minus is already proportional to a single scattering cross-section. That's already very good. That's already close to AGK, but it depends still on the saturation scale, which by itself depends on this connection number. And a similar equation or similar formula we drew then for the PT distribution, because we can deduce them from this x plus x minus distribution. Now, what is the effect of the N-con dependence of the Q sat? So if we have, looking now at the PT distributions, if we have an increasing saturation scale, that means we have more and more suppression of low PT partons. But for large PT, nothing changes. And that's the important thing here. If we are only interested in high PT for the moment, then we can replace the Q sat by some constant, which we call Q0. And this is just the maximum of all relevant saturation scales. And then we can simply make the sum of all these different contributions for the different connection numbers. And then we can finally get to the result that the inclusive cross-section for nucleus for minimum bias is then equal A times B times the single scattering cross-section with a Q0 cutoff. And this means this formula is AGK, but we call this generalized AGK stream, but only for high PT. That's only for the Q0s bigger than all the relevant saturation scales. And that's extremely important. I mean, one gets factorization in PP and in nucleus for inclusive cross-sections high PT in a fully self-consistent multiple parallel scattering scheme. And with what I think which is mandatory to include energy momentum conservation, to construct really parallel scattering, to do theory which is really the basis of Monte Carlo, and finally as a boundary condition kind of have factorization at high PT. And to show this here explicitly, I show you the plot which you have seen before. And I add on the plot now by the red points the simulation results for the full multiple scattering result, the full Monte Carlo multiple scattering. You see at high PT, they're identical. Here around 20, one has a little bit overshooting, which is coming from intrinsic PT, but otherwise at high PT, kind of the full scale multiple scattering Monte Carlo and the single Pomeroy result, single scattering result, they are identical. At low PT, of course, it's quite different. So it's only true for high PT. I mean, I do all this not because I'm so terribly interested in high PT, but it's a boundary condition. So you have to prove that in order to have a model which is reasonable and which is not in contradiction by itself. which it would be otherwise. And now I think this is really very useful to understand why all this works. Let's here consider the deuteron-deuteron scattering, so two small nuclei. And here we have first a double scattering between two nucleons. And here the third diagram here is a single scattering between two other nucleons. If I compare the two left scatterings to the right one, we first see that the n-con, the connection number, is bigger for the two left ones because it's 2. So we have a double scattering. For the right one, it's 1. Then for the left ones, the energy has to be smaller. And this I indicate by the smaller boxes. So there should be something around the half of the energy of the right one, which does not share energy. On the other hand, the Q sat for the left ones here has to be bigger. I indicate this here by the red points, which are bigger than the red point here. So we have a bigger saturation scale, which means the evolution is shorter. But now all that has been done such that the central part does not change. So the energy is changed, the Q sat changed, but the central part in all these three contributions is the same. And that's why it works. And the particle production, this has then really consequences. So the particle production will be harder if it's coming from these processes on the left. Now, implementing both energy momentum conservation and saturation is really needed. So the one compensates the other. So that's really the most important message of my talk here, without really discussing little details and how well it works in detail for a given observable. But this is more a fundamental thing. Now, the nonlinear effects happen very early. So here again, my plot I showed in the very beginning. If I look at with a magnifying glass, very early we have this fusion process, this nonlinear effects where we have gluon-gluon fusion since the parton densities are so high. So here, this saturation stuff is happening long before the overlap, the red point. Whereas initial state, this is an initial state phenomenon. And this is contrary to final state, like the string manipulations as color reconnection, which have to some extent a very similar effect concerning observables. But physics-wise, it's completely different. So in one sense, it's very, very early stage. In the other case, it's final one. Now, I didn't really plan to say much about the secondary interactions because I don't have the time, so I want to get to the end. The secondary interactions are very important in practice, and it's a solid basis. Now with the EPOS4, as I explained, for the primary interactions, is a very solid basis now for the setting the stage what follows, which are then secondary interactions like co-corona separation, and the coarse and the dense stuff, which then has a hydro type evolution and the microcanonical decay and statistical particle production and all that. And at the end, we have hadronic cascade. So all this would be a talk by itself. But really the real new stuff is this first part. And we think for the first time, we have really something which is now at least self-consistent. And so I do not really talk about the second part, but here I show you the EPOS documentation. We have a web page, and I invite you to look in particular at our papers section here. And we prepared already lots of papers since last year when it became public. The first four papers are about really the basics of EPOS4, and then we have applications about EPOS4 and heavy quark with interactions of heavy quarks with the plasma phase. So these are the papers on the bottom of this list. And now coming to my summary, there are ad hoc assumptions and details may be questions, but the overall multiple scattering picture, I really think, seems mandatory since they are based on very fundamental principles, which is this parallel scattering. I mean, if you have a reaction or an overlap time of 0, then what else can be than having things in parallel? There's nothing like first and second. Then there's energy momentum sharing, and for particle production that is important, and one cannot simply ignore that, but although it's done quite often. Then one needs to implement saturation in some way or the other, and it seems mandatory to implement this kind of environment-dependent factorization scales, which compensate exactly the effect of the energy momentum scaling, as I try to explain you in detail. So it's not certain that all the details are correct, but the overall picture, I think, it should be like that. we have in addition the validity of factorization at high PT. It must be like that. So it should be a boundary condition for any model. And really important for us, our theoretical framework is really the basis of the Monte Carlo, and not only something which kind of suggests to do something similar. So if we have energy conservation in the Monte Carlo, we do have energy conservation already in the underlying theory, which is not always, or which is usually not the case. Now, we think we have a solid basis for further activities, which is first the systematic improvements of EPOS4, which was never done before on EPOS3. So as we still have to work on that. We have further projects at EPOS4 heavy quark, EPOS4 and jets. And finally, if Tanguy wants to also work on that, create a fast version, which exists already, but not yet kind of tuned for cosmic ray applications. But all this is doable to be used for error shower simulations. But this is kind of the next project. And I think that's a good point to stop. And thank you very much.
Okay, thank you, Klaus. So the time is over, but maybe we have time for 2 questions. Yes, please.
Oh, thanks, Klaus. That is very interesting. And let me ask a naive question as an experimentalist. So I've grown up with the concept of formation time, coherence length, rescattering, and time it takes for formation and fission of strings. And we should throw that overboard in this new fundamental.
I can hear you not so well. Can you speak a bit louder?
Okay, so can you understand me now?
Yes.
Okay, Klaus, it's me, Karl-Heinz. So I'm asking about the.
Yeah, I see. I know.
Okay. I'm asking about the concept of which I was known or I learned the concept of formation time, coherence length, rescattering time it takes for formation and fission of strings and all these kind of things. So you say
yes,
fundamentally incorrect that concept.
But this is kind of stuff which concerns the final stage. So I was talking about the initial stage.
Okay, so that is my.
So I think this is really the most important thing. We have to distinguish between what happens initially. I think that's really the challenge because, as I said in one of my last transparencies, there are many things which you can explain from model side with doing something in initial stage or in final stage.
Okay.
And I think the challenge is really to separate the two. And I think it's difficult to do it only from the experimental side. And therefore, I really think it's important to look a little bit into the theoretical things. And that's why here I made a little bit of theoretical discussion about what is really inside the model.
Okay, thank you.
And then there is also another one from Zoom. That will be all. Please.
At the moment, I don't hear anything.
Respected Professor Werner, your lecture was outstanding and clear-cut lecture. You have conveyed beautiful physics, and personally, I am very much proud of you. Really excellent lecture you have given, and I am very happy. You conveyed a beautiful message to all the scientists in the world.
Okay.
Comment, please, Ralph.
Okay, Klaus, this is Ralph. Yeah. So a quick question. First of all, yeah, the talk was really very, very clear and very nice. Now, how
Thank you.
is it if you look at processes that have large and that have small cross sections, like let's say lepton pair production or quark antiquark or whatever production, one being a large cross section and one being essentially a tiny one.
Yes.
Or almost like Higgs. Because your multiplication factor is independent of that, isn't it? Like so I'm asking whether I see that technically what you do is exactly the right thing. You want to get the cross-section reproduced. And now the question is whether the way you do it is really reflecting the physics to me.
Yes.
So I'm looking for a process where I would expect one could see easily the saturation and everything, and other processes where one might not see it, because it's a rare process by itself. So it's so you don't expect any multiple effects. And is that automatically taken care of?
But I mean, everything concerning this factorization stuff, that essentially we get one. So all this concerns kind of rare processes. I mean, if and this is only done as a test. So I was using here high PT, but you could take some rare processes which works in the same way. But I mean, all that really, in principle, this is relevant for rare processes. And but I consider this as kind of a boundary for my model to do it overall right, even if I'm at the end looking at kind of less rare processes, what we are usually more interested in.
Yeah, okay. But so we won't have the time to discuss this really here because you're also not here and the coffee break would be.
Yeah, unfortunately.
It's but I think there are a few things that you predict that where you go from the single scattering to like 1.1, 1.2, that is a non-trivial prediction how you do the correction, and that,
Okay.
that one can actually use to test whether that's
Okay.
approach. But,
Okay, thank you.
We close the session of questions. We thank also to Klaus about this presentation. Thank you.
Sure.